1,200 light-years from Earth, a planet orbits quietly around an orange dwarf star. Its surface gravity is just 30% stronger than Earth's, its size only 2.36 times larger than our home world. But what makes this planet extraordinary isn't its similarities to Earth. It's how it might be even better for life than our own world. This is Kepler 442b, and it sits perfectly within its star's habitable zone, receiving just the right amount of energy to maintain liquid water on its surface. The star it orbits is more stable than our Sun, producing less harmful radiation while maintaining steady energy output for billions of years longer than our own star will live. Its stronger gravity could help maintain a thicker atmosphere, protecting any life on its surface more effectively than Earth's atmosphere protects us. The discovery of Kepler 442b was just the beginning. Our telescopes have revealed an entire galaxy teeming with potential Earth 2.0s. From the 7 Earth-sized planets of TRAPPIST-1 dancing in perfect orbital resonance to our closest neighbor, Proxima Centauri b, where powerful magnetic fields paint the skies with eternal auroras. Through the eyes of humanity's most advanced instruments, Kepler, TESS, and the James Webb Space Telescope, we're uncovering worlds that defy our imagination, super-Earths with oceans hundreds of miles deep, and systems that challenge everything we thought we knew about how worlds like ours form and evolve. These aren't theoretical possibilities or scientific speculation. These are real places, detected and studied by our most sophisticated technology, each one bringing us closer to answering humanity's most profound question: are we alone in the universe? Before we dive deep into these extraordinary discoveries, I want to take a moment to connect with you. Creating videos that explore these groundbreaking discoveries requires hundreds of hours of research and production. If you want to join us on this journey through the cosmos, please support Space Mysteries by subscribing and liking this video. It helps us continue bringing you the latest breakthroughs in our understanding of the universe for free. Now let's begin our journey through the most extraordinary planetary discoveries in human history and uncover what I found during my 90-day research. The story of how we began finding other worlds is one of persistence, innovation, and technological breakthrough. In 1992, astronomers made a discovery that would forever change our understanding of the cosmos, the first confirmed planets outside our solar system. These weren't the Earth-like worlds we were hoping for. They were planets orbiting a pulsar, a dead star's rapidly spinning corpse. But this discovery opened the floodgates of possibility. The real revolution began in 1995 with a discovery that shook the foundations of planetary science. Michel Mayor and Didier Queloz detected 51 Pegasi b, the first planet ever found orbiting a star similar to our Sun. This massive world, roughly half the mass of Jupiter, orbited its star in just 4 days, a concept that completely contradicted our theories of planetary formation. We had expected to find other solar systems that mimicked our own, with small rocky worlds close to their stars and gas giants in distant orbits. Instead, we found what we now call a hot Jupiter, a massive gas giant practically skimming the surface of its star. This discovery forced us to completely reimagine how planetary systems form and evolve. The presence of these hot Jupiters suggested that planets could migrate dramatically from their birth locations, drawn inward by the gravitational forces of their nascent stellar systems. This single discovery transformed our understanding of planetary dynamics and launched us into a new era of astronomical research. The methods we used to find these worlds were equally revolutionary. The primary technique, known as the radial velocity method, relies on detecting the minute wobble in a star's motion, caused by an orbiting planet's gravitational pull. This wobble creates subtle shifts in the star's spectrum, the rainbow of light we see when starlight is split apart. When a star moves slightly toward Earth, its spectral lines shift toward the blue end of the spectrum. When it moves away, they shift toward the red. These shifts can be as small as a few meters per second, about the speed of a human walking. But this method had limitations. It preferentially detected massive planets close to their stars, as these created the largest wobbles. Finding Earth-sized worlds would require new techniques and technologies. Enter the transit method, which would eventually revolutionize our search for other Earths. The transit method works by detecting the tiny dip in a star's brightness when a planet passes between the star and our telescopes. This technique allows us to measure not just a planet's presence, but also its size and, in some cases, even analyze the composition of its atmosphere. The challenge? The dip in brightness caused by an Earth-sized planet is minuscule, less than 1/10,000th of the star's total light. The breakthrough came with the development of highly precise photometers, instruments capable of measuring stellar brightness with unprecedented accuracy. These devices could detect variations in starlight as small as a few parts per million, making it possible to spot Earth-sized planets for the first time. The real game-changer was the introduction of space-based telescopes dedicated to planet hunting. Free from the distorting effects of Earth's atmosphere, these instruments could maintain the steady gaze needed to detect the faintest planetary signals. This approach led to the development of increasingly sophisticated detection methods, including gravitational microlensing and direct imaging. Gravitational microlensing takes advantage of Einstein's theory of general relativity, detecting planets by observing how their gravity bends and focuses light from background stars. This technique is unique in its ability to find planets at greater distances from Earth and even free-floating planets that don't orbit any star. Direct imaging, while extremely challenging, has provided some of our most dramatic discoveries. By carefully blocking out the overwhelming light of a star, we can actually see some planets directly. These tend to be young, massive worlds that still glow with the heat of their formation, but each one provides invaluable information about planetary evolution and composition. As our methods evolved, so did our understanding of planetary statistics. We discovered that planets are not rare anomalies in the cosmos. They're the rule. Current estimates suggest that, on average, every star in our galaxy hosts at least one planet. With roughly 200 billion stars in the Milky Way alone, we're looking at a minimum of 200 billion planets in our galaxy. The implications are staggering. The data has revealed patterns we never expected. We found that the most common type of planet in our galaxy isn't like anything in our solar system. They're super-Earths, or mini-Neptunes, worlds that bridge the gap between rocky planets and gas giants. These planets, typically between 2 and 4 times the size of Earth, have no analog in our solar system, yet they appear to be the galaxy's preferred planetary size. What's particularly fascinating is how our planet-hunting capabilities have evolved to detect increasingly smaller and more Earth-like worlds. The first exoplanets we found were Jupiter-sized behemoths, but today we can detect planets smaller than Earth. This progression has been exponential, driven by both technological advancement and improved analytical techniques. Modern detection methods now combine multiple approaches, cross-referencing data from different telescopes and techniques to confirm discoveries. This has led to a dramatic decrease in false positives and an increased confidence in our findings. We've moved from merely detecting planets to characterizing their basic properties: mass, radius, density, orbital characteristics, and even atmospheric composition. The revolution in planet hunting has transformed our perspective on our place in the cosmos. We now know that planetary systems come in an incredible variety of configurations, many of which challenge our preconceptions about how solar systems should look. This diversity suggests that the path to forming habitable worlds might be more varied than we initially thought, opening up new possibilities in our search for Earth 2.0. The Kepler Space Telescope, launched in 2009, marked the beginning of a new epoch in humanity's search for other worlds. Named after the 17th century astronomer Johannes Kepler, who discovered the laws of planetary motion, this remarkable instrument was designed with a singular purpose: to determine how common Earth-like planets are in our galaxy. What followed was a revolution in our understanding of the cosmos that would forever change our perspective on our place in the universe. Kepler's approach was revolutionary in its simplicity. The telescope stared unblinkingly at a single patch of sky between the constellations Cygnus and Lyra, monitoring the brightness of over 150,000 stars simultaneously. This region was carefully chosen to represent a typical slice of our Milky Way galaxy, containing stars of various ages and types. The field of view was roughly equivalent to holding your hand at arm's length, covering about 0.28% of the sky. A tiny window that would reveal an unprecedented view of our galaxy's planetary population. The engineering behind Kepler was a marvel in itself. The spacecraft's photometer, essentially a 95-megapixel camera, was the largest ever launched into space at that time. Its precision was extraordinary, capable of detecting a change in brightness equivalent to a fly passing in front of a car's headlight thousands of miles away. This incredible sensitivity was necessary to detect the minute dimming of starlight caused by transiting planets. The numbers that emerged from Kepler's observations were nothing short of astounding. In its primary mission alone, Kepler identified 2,662 confirmed planets and an additional 2,350 candidate planets awaiting confirmation. The sheer volume of discoveries transformed our understanding of planetary demographics, revealing that planets are far more numerous and diverse than anyone had imagined. This wealth of data allowed scientists to begin constructing the first meaningful statistics about planetary populations. The mission's impact on our understanding of planetary formation was revolutionary. Prior to Kepler, our theories of planet formation were based largely on our solar system, the only example we had. Kepler showed us that our solar system, with its well-spaced planets in nearly circular orbits, might be the exception rather than the rule. The telescope discovered numerous systems with architectures that challenged our fundamental theories about how planets form and evolve. One of the most startling discoveries was the prevalence of hot Jupiters and warm Neptunes, massive planets orbiting perilously close to their stars. These worlds, with orbital periods of mere days or weeks, forced astronomers to completely revise their understanding of planetary migration. The presence of these planets suggested that massive worlds could form far from their stars and migrate inward through complex gravitational interactions with their natal protoplanetary disks. Perhaps Kepler's most significant contribution was its ability to detect smaller, rocky planets. Previous surveys had been biased toward finding large gas giants, but Kepler's unprecedented precision allowed it to spot planets as small as Mercury. This capability led to the groundbreaking realization that rocky planets are not rare curiosities, but common features of planetary systems. The data revealed that small rocky planets are actually more numerous than their larger gaseous cousins, a finding that dramatically improved our odds of finding potentially habitable worlds. The data revealed a fascinating pattern in the sizes of planets, leading to one of Kepler's most profound discoveries, the Radius Valley, or Fulton Gap. This mysterious gap occurs between planets roughly 1.5 and 2 Earth radii in size. The existence of this gap suggests that there are two distinct populations of small planets: super-Earths, rocky worlds up to 1.5 times Earth's radius, and mini-Neptunes, gas-enveloped worlds larger than 2 Earth radii. This dichotomy has profound implications for our understanding of planetary formation and evolution, suggesting that certain planetary sizes are preferred by nature, while others are rare or impossible. Kepler's observations also revolutionized our understanding of planetary system architecture. The telescope discovered numerous compact systems where multiple planets orbit their star in close proximity. The most famous of these is Kepler 11, which hosts 6 planets orbiting closer to their star than Venus orbits our Sun. These tightly packed systems challenged our models of planetary formation and evolution, forcing astronomers to reconsider how stable such configurations could be over long periods. The mission's impact on our understanding of habitable worlds was particularly significant. By combining Kepler's planet detection statistics with our understanding of stellar properties, astronomers could estimate that approximately 20 to 30% of Sun-like stars host potentially habitable Earth-sized planets. This means that in our galaxy alone, there could be billions of worlds with conditions similar to Earth. This finding transformed the search for extraterrestrial life from a speculative endeavor into a data-driven science. The concept of the habitable zone gained new significance through Kepler's observations. The mission showed that planets in this life-friendly region are not rare anomalies, but relatively common occurrences. Moreover, Kepler's data allowed scientists to refine their understanding of what makes a planet potentially habitable. The discovery of planets in extreme orbits or unusual configurations expanded our conception of where life might be possible. One of Kepler's most unexpected contributions was its impact on stellar physics. The continuous monitoring of thousands of stars led to breakthroughs in asteroseismology, the study of stellar interiors through surface vibrations. This improved our ability to determine stellar properties with unprecedented precision, which in turn enhanced the accuracy of planetary measurements. The mission effectively created a new field of study, combining stellar and planetary science in ways never before possible. Kepler also pioneered new techniques for data analysis that continue to influence exoplanet research. The telescope's vast dataset led to the development of sophisticated algorithms for detecting planetary signals amid stellar noise. These methods have become standard tools in modern astronomical research, enabling discoveries by other telescopes and missions. The mathematical and computational techniques developed to analyze Kepler data have applications far beyond astronomy, influencing fields from medical imaging to climate science. The mission discovered several bizarre planetary systems that defied conventional wisdom. It found planets orbiting evolved stars, worlds caught in the process of disintegration due to intense stellar radiation, and systems with planets in highly eccentric orbits. Each of these discoveries expanded our understanding of what's possible in planetary evolution. Particularly intriguing were the discoveries of circumbinary planets, worlds that orbit 2 stars instead of 1. Kepler 16b, nicknamed Tatooine, became the first confirmed circumbinary planet, proving that planets can form and maintain stable orbits in what were previously thought to be highly challenging gravitational environments. When Kepler's primary mission ended due to the failure of its reaction wheels in 2013, NASA engineers devised an ingenious solution using solar pressure to help stabilize the spacecraft. This led to the K2 mission, which, despite its limitations, added hundreds more planetary discoveries and expanded our view of planetary diversity across different stellar populations and galactic environments. The revolution initiated by Kepler continues to reverberate through astronomical research. Its vast data set remains a treasure trove, with new discoveries still emerging from reanalysis using improved techniques. The mission's findings have fundamentally altered our perspective on planetary systems, showing us that our cosmic neighborhood is far more diverse and populated than we ever imagined. Kepler's legacy extends beyond its numerical achievements. It transformed our understanding of our place in the cosmos and set the stage for the next generation of exoplanet exploration. Most importantly, Kepler showed us that we live in a galaxy teeming with planets, many of which might be similar to Earth. This discovery has profound implications for humanity's future and our search for life beyond Earth. The Kepler Revolution wasn't just about finding other worlds. It was about understanding our own place in a universe far richer in planets than anyone had dared to imagine. Among the thousands of exoplanets discovered, Kepler 442b stands as one of the most intriguing candidates for a potential Earth analog. Located approximately 1,206 light-years away in the constellation Lyra, this super-Earth has captured the imagination of scientists and challenges our understanding of planetary habitability. Kepler 442b orbits a K-type orange dwarf star, which is significantly cooler and smaller than our Sun. While this might seem disadvantageous for life as we know it, K-type stars actually possess several characteristics that could make them superior hosts for habitable planets. These stars are more stable than Sun-like stars, producing less harmful ultraviolet radiation, while maintaining steady energy output for billions of years longer than our Sun will. The planet itself is approximately 2.34 times Earth's radius and has an estimated mass of about 2.36 Earth masses. This places Kepler 442b firmly in the category of super-Earths, but with fascinating implications. Its density calculations suggest a rocky composition, unlike many planets of similar size, which tend to be gaseous mini-Neptunes. The higher mass creates a stronger gravitational field, approximately 1.3 times that of Earth's surface gravity. This stronger gravity could help the planet retain a substantial atmosphere, crucial for potential habitability. What makes Kepler 442b particularly special is its position within its star's habitable zone. The planet orbits its star every 112.3 Earth days, receiving about 70% of the stellar energy that Earth receives from the Sun. This places it comfortably within the conservative habitable zone, the region where liquid water could exist on the surface under the right atmospheric conditions. Unlike many potentially habitable exoplanets, Kepler 442b isn't tidally locked to its star, meaning it likely experiences a day-night cycle similar to Earth's, albeit with different durations. The planet's larger size presents intriguing possibilities for geological activity. With greater mass comes increased internal heat retention, potentially leading to more vigorous plate tectonics than Earth experiences. This enhanced geological activity could create a more robust carbon cycle, crucial for maintaining stable surface temperatures over long periods. The stronger gravity would likely result in a flatter surface topography, potentially leading to shallower oceans spread over more of the planet's surface. Atmospheric modeling of Kepler 442b suggests it could maintain a stable atmosphere despite its proximity to its star. The planet's escape velocity is estimated at 15.6 kilometers per second, significantly higher than Earth's 11.2 kilometers per second. This increased escape velocity means the planet can hold on to lighter atmospheric molecules more effectively than Earth, potentially maintaining a thicker atmosphere that could help distribute heat more evenly across its surface. The composition of Kepler 442b's potential atmosphere is a subject of intense scientific speculation. Given its mass and position in the habitable zone, models suggest it could maintain an atmosphere similar to Earth's, but potentially denser. This denser atmosphere could create a more efficient greenhouse effect, helping to maintain stable surface temperatures despite receiving less stellar energy than Earth does from the Sun. One of the most fascinating aspects of Kepler 442b is its potential for water retention. The planet's higher gravity would affect the behavior of any surface water, potentially creating global patterns significantly different from Earth's. Ocean waves would likely be smaller but more energetic, and the atmospheric circulation patterns would create different precipitation systems than what we're familiar with on Earth. The magnetic field of Kepler 442b, predicted to be stronger than Earth's due to its larger mass and potentially more active core, could provide crucial protection against its star's radiation. This magnetic shield would be essential for protecting any potential atmosphere and surface water from being stripped away by stellar winds, a common fate for planets orbiting closer to their stars. The potential for life on Kepler 442b presents unique considerations. The stronger gravity would influence the evolution of any potential life forms, possibly leading to shorter, more robust organisms than those found on Earth. The different day-night cycle would require unique adaptations for any photosynthetic organisms, and the stronger gravity might favor life forms that spread horizontally rather than vertically. Seasonal variations on Kepler 442b would differ significantly from Earth's. With its 112.3-day orbit, seasons would be shorter, but potentially more intense. The planet's axial tilt, though not precisely known, would play a crucial role in determining the severity of these seasons. This could create unique evolutionary pressures for any potential life forms, requiring adaptations to more rapid environmental changes. The study of Kepler 442b has revolutionized our understanding of planetary habitability. It demonstrates that potentially habitable worlds don't need to be exact Earth twins. They can be significantly larger and orbit different types of stars while still maintaining conditions conducive to life as we know it. This realization has expanded our search parameters for habitable worlds and challenged our Earth-centric view of what makes a planet livable. The implications of Kepler 442b's discovery extend beyond just finding another potentially habitable world. It represents a new class of super-Earth that exists in a sweet spot between truly Earth-like planets and mini-Neptunes. These planets could potentially combine the best aspects of both. The rocky composition necessary for life as we know it, with the added benefits of stronger gravity and magnetic fields that could make them even more stable environments than Earth. Current limitations in our observational capabilities mean we can't yet directly detect the presence of an atmosphere or determine its composition. However, upcoming telescopes and observation methods are being designed with planets like Kepler 442b in mind. These future missions will attempt to analyze the atmospheric composition of super-Earths, potentially revealing the presence of biosignatures that could indicate the presence of life. Kepler 442b stands as a testament to the diversity of potentially habitable worlds in our galaxy. It challenges our assumptions about what makes a planet habitable and suggests that the conditions for life might be more flexible than we initially thought. As our understanding of this remarkable world continues to grow, it may help us answer one of humanity's most profound questions. How unique is the life-supporting environment of Earth in the cosmic scheme of things? The discovery of the TRAPPIST-1 system in 2017 marked a watershed moment in our search for potentially habitable worlds. Located just 39 light-years away in the constellation Aquarius, this system presents an unprecedented laboratory for studying the diversity and potential habitability of Earth-sized worlds. Unlike any planetary system we've encountered before, TRAPPIST-1 challenges our understanding of planetary formation and evolution, while offering tantalizing possibilities for future exploration. At the heart of this remarkable system lies TRAPPIST-1, an ultra-cool dwarf star merely 9% the mass of our Sun and barely larger than Jupiter. This tiny star, technically classified as a type M8V red dwarf, burns at a relatively cool temperature of about 2,566 Kelvin. Despite its diminutive size, this star hosts a spectacular system of 7 Earth-sized planets, all orbiting closer to their star than Mercury orbits our Sun. This compact arrangement creates a unique cosmic choreography that has captured the imagination of astronomers worldwide. The planets of TRAPPIST-1, designated alphabetically from B to H, represent the largest known collection of Earth-sized worlds orbiting a single star. Their sizes range from 75% to 110% of Earth's radius, making them remarkably similar to the terrestrial planets in our solar system. This similarity in size suggests these worlds are likely rocky rather than gaseous, marking them as prime candidates for detailed study of potentially habitable environments. The orbital dynamics of the TRAPPIST-1 system are nothing short of extraordinary. The planets exist in a state of orbital resonance, meaning their gravitational interactions create stable, rhythmic patterns that have likely persisted for billions of years. This resonance chain is one of the longest ever discovered, with each planet's orbital period relating to its neighbors in simple mathematical ratios. For instance, for every 8 orbits TRAPPIST-1b completes, planet C completes 5, planet D completes 3, and so on through the system. This orbital resonance has profound implications for the system's evolution and stability. The gravitational dance between the planets helps maintain their orbits while potentially driving tidal heating in their interiors. This additional heat source could maintain geological activity and potentially create conditions favorable for life, even on worlds that might otherwise be too cold or too hot. The compactness of the TRAPPIST-1 system defies our traditional understanding of planetary formation. All 7 planets orbit within 0.06 astronomical units of their star, a distance less than 1/5 of Mercury's orbit around the Sun. This tight configuration means that from the surface of any TRAPPIST-1 planet, the neighboring worlds would appear larger in the sky than our Moon appears from Earth. The planets' close proximity to each other also suggests they likely influence each other's climates through gravitational interactions and potentially even atmospheric transfer. 3 of the TRAPPIST-1 planets, E, F, and G, orbit within the star's theoretical habitable zone. However, the concept of habitability in this system is more complex than in our solar system. The planets are likely tidally locked, meaning they always present the same face to their star, creating permanent day and night sides. This tidal locking could create extreme temperature differences between the hemispheres, potentially leading to powerful atmospheric circulation patterns that could either help or hinder habitability. TRAPPIST-1e, often considered the most promising candidate for habitability, receives about the same amount of stellar energy as Earth does from the Sun. Detailed observations suggest it has a rocky composition and could potentially host liquid water on its surface. Its radius is 91% of Earth's, and its mass is about 77% of Earth's, giving it a surface gravity similar to what we experience on Earth. These characteristics make it one of the most Earth-like exoplanets yet discovered. The system's proximity to Earth makes it an ideal target for atmospheric characterization. Early observations using the Hubble Space Telescope and ground-based instruments have already provided tantalizing hints about the planet's compositions. The data suggests that the inner planets, particularly B and C, may have lost their original atmospheres due to intense stellar radiation, while the outer planets could retain substantial atmospheres rich in molecular hydrogen or heavier elements. The extreme ultraviolet radiation from TRAPPIST-1 presents both challenges and opportunities for potential life. While the radiation levels are higher than what Earth receives, the planet's atmospheres, if present, could provide adequate protection. Moreover, the red dwarf's radiation peaks at longer wavelengths than our Sun's, potentially allowing for unique forms of photosynthesis that could utilize infrared light rather than visible light. Water content on the TRAPPIST-1 planets has been a subject of intense study. Density measurements suggest that some of the planets could contain significant amounts of water, up to 5% of their mass. This is substantially more than Earth's water content, about 0.02% by mass. These water worlds could have global oceans hundreds of kilometers deep, creating unique environmental conditions unlike anything in our solar system. The age of the TRAPPIST-1 system, estimated to be between 3 and 8 billion years, suggests these planets have had ample time to develop complex chemistry and potentially even life. The system's age also indicates remarkable stability, as the planets have maintained their intricate orbital dance for billions of years despite their close proximity to each other. Magnetic field interactions in the TRAPPIST-1 system present another fascinating area of study. The star's magnetic field is much stronger than our Sun's, and the planets orbit within this powerful magnetic environment. This could lead to complex magnetospheric interactions, potentially creating auroral displays far more spectacular than Earth's northern lights. These magnetic fields might also play a crucial role in protecting any planetary atmospheres from stellar wind erosion. The possibility of atmospheric exchange between the TRAPPIST-1 planets adds another layer of intrigue to the system. Given their close proximity, material ejected from one planet's atmosphere through meteorite impacts or volcanic activity could potentially reach neighboring planets. This raises the fascinating possibility of material exchange between potentially habitable worlds, similar to how meteorites from Mars have reached Earth. Recent studies have begun to explore the potential for photochemistry in the TRAPPIST-1 system. The star's unique spectral energy distribution could drive chemical reactions different from those we see in our solar system. This could lead to the formation of complex organic molecules through pathways not possible under our Sun's illumination, potentially creating conditions favorable for the emergence of life. The discovery and study of the TRAPPIST-1 system have broader implications for our understanding of planetary systems around low-mass stars. Such stars are the most common type in our galaxy, comprising about 75% of all stars in the Milky Way. If systems like TRAPPIST-1 are common, the implications for the prevalence of potentially habitable worlds are staggering. The future study of TRAPPIST-1 holds enormous promise. New telescopes and observation techniques will allow us to characterize the planet's atmospheres, search for signs of geological activity, and potentially even detect signatures of life. The system's proximity makes it an ideal target for future interstellar probes, should such technology be developed. The TRAPPIST-1 system represents more than just another planetary system. It's a window into the diversity of worlds that exist in our galaxy. It challenges our assumptions about how planetary systems form and evolve, while offering multiple opportunities to study potentially habitable environments. As we continue to study this remarkable system, it may help us answer fundamental questions about the prevalence of life in the universe and our place within it. The discovery of Proxima Centauri b in 2016 marked a pivotal moment in our search for potentially habitable worlds. Located just 4.2 light-years from Earth, this planet represents our closest opportunity to study an Earth-sized world beyond our solar system. Its proximity makes it not only a prime target for detailed scientific investigation, but potentially humanity's first destination for interstellar exploration. Proxima Centauri b orbits a red dwarf star called Proxima Centauri, the smallest and faintest star in the Alpha Centauri system. This triple star system consists of the binary pair Alpha Centauri A and B, with Proxima Centauri orbiting far from this central pair. Proxima Centauri is a red dwarf star, merely 12% the mass of our Sun, and radiating just 0.17% of the Sun's energy output. This tiny stellar ember, despite its modest size, holds the key to understanding one of the most intriguing planetary systems in our cosmic neighborhood. The planet's discovery utilized the radial velocity method, detecting the minute wobble in Proxima Centauri's motion caused by the planet's gravitational pull. The precision required to detect this signal was extraordinary, measuring stellar movements of just 1.38 meters per second, about the speed of a human walking. This detection pushed the boundaries of astronomical instrumentation and demonstrated the remarkable advancement in our planet-hunting capabilities. The planet's orbit presents one of its most intriguing features. Proxima b completes an orbit every 11.2 Earth days, placing it just 0.049 astronomical units from its star, roughly 1/13 of Earth's distance from the Sun. Despite this close proximity, the planet receives about 65% of the energy Earth receives from the Sun, placing it squarely within its star's habitable zone. This seemingly paradoxical situation arises from Proxima Centauri's low luminosity, creating a habitable zone much closer to the star than in our solar system. The implications of this tight orbit extend far beyond simple energy calculations. Proxima b is almost certainly tidally locked to its star, meaning one hemisphere experiences eternal daylight while the other remains in perpetual darkness. This configuration creates extreme environmental conditions unlike anything in our solar system. The day side potentially faces temperatures hot enough to melt lead, while the night side might be cold enough to freeze carbon dioxide into dry ice. However, recent atmospheric modeling has revealed potential mechanisms that could moderate these temperature extremes. A thick atmosphere with the right composition could efficiently distribute heat from the day side to the night side through powerful wind systems. These models suggest that if Proxima b maintains a substantial atmosphere, broad regions of its surface could sustain temperatures compatible with liquid water. The question of Proxima b's atmosphere is particularly crucial, given its star's volatile nature. Red dwarfs like Proxima Centauri are notorious for their violent flares and stellar eruptions, particularly in their youth. Early in its history, Proxima b likely faced stellar flares hundreds of times more powerful than anything Earth experiences, potentially stripping away its primordial atmosphere. Whether the planet could have regenerated an atmosphere through volcanic activity or retained its original atmosphere through a strong magnetic field remains one of the most pressing questions in its study. Recent research has focused on Proxima b's potential magnetic field strength. The planet's mass suggests it could maintain an active liquid core, potentially generating a magnetic field stronger than Earth's. This enhanced magnetic protection might be crucial for retaining an atmosphere and protecting any potential surface life from its star's intense radiation. The possibility of life on Proxima b presents unique considerations. Any organisms would need to adapt to constant light or darkness, depending on their location, and cope with higher radiation levels than Earth life experiences. The potential for photosynthesis exists, but might utilize different wavelengths than Earth plants, possibly adapting to infrared radiation that penetrates the atmosphere more effectively. The stronger gravity might favor low-profile life forms, while the possible intense wind patterns could influence the evolution of both flora and fauna. The star's age, estimated at 4.85 billion years, suggests Proxima b has had ample time for complex chemistry and potential biological evolution. However, the planet's early history likely included a period of intense stellar activity that could have sterilized its surface. Whether life could have emerged after this initial hostile period or survived in underground environments remains a fascinating question. The study of Proxima b has spawned new theoretical frameworks for understanding planetary habitability. Its unique characteristics have forced scientists to reconsider what conditions are truly necessary for life, leading to expanded definitions of habitable environments. This has influenced the search for potentially habitable worlds around other red dwarf stars, which comprise about 75% of our galaxy's stellar population. The proximity of Proxima b makes it an ideal candidate for future direct imaging and atmospheric characterization missions. Proposed space telescopes and ground-based observatories might be able to detect the presence of atmospheric gases that could indicate biological activity. The planet's location also makes it a prime target for potential interstellar probes, with projects like Breakthrough Starshot proposing to send tiny spacecraft to study the Proxima Centauri system. Recent observations have hinted at the possibility of additional planets in the Proxima Centauri system, suggesting Proxima b might be part of a more complex planetary system. The gravitational interactions between multiple planets could affect Proxima b's orbit and rotation, potentially influencing its long-term habitability. Understanding these dynamics could provide crucial insights into the formation and evolution of planetary systems around red dwarf stars. Every new discovery about this world helps refine our understanding of similar planets throughout the galaxy, bringing us closer to answering fundamental questions about our cosmic neighborhood and humanity's place within it. The dawn of the 2020s marked the beginning of a new era in exoplanet research, characterized by revolutionary technologies and observation methods that promise to transform our understanding of distant worlds. While previous generations of planet-hunting tools focus primarily on detection, this new wave of technology aims to reveal the intimate details of exoplanet characteristics, from atmospheric composition to surface conditions. The James Webb Space Telescope, or JWST, represents the pinnacle of this new generation of planet-hunting technology. Operating at infrared wavelengths, JWST's capabilities go far beyond simple planet detection. Its unprecedented sensitivity allows it to analyze the chemical fingerprints of exoplanet atmospheres with extraordinary precision. The telescope's unique position at the Earth-Sun L2 Lagrange point, combined with its sophisticated sun shield, enables it to maintain the ultra-cold temperatures necessary for cutting-edge infrared observations. JWST's NIR spec, or Near-Infrared Spectrograph instrument, has revolutionized atmospheric analysis of exoplanets. This instrument can simultaneously observe multiple wavelengths of light, creating detailed chemical profiles of planetary atmospheres during transits. The spectrograph's micro-shutter array, containing over 250,000 individually controlled shutters, allows it to observe multiple targets simultaneously while blocking out unwanted light from nearby stars. The MIRI, or Mid-Infrared Instrument, capabilities of JWST have opened new windows into exoplanet research. Operating at longer wavelengths than NIR-SPEC, MIRI can detect thermal emission directly from cooler planets and brown dwarfs. This ability to measure heat signatures directly from planets provides crucial information about atmospheric circulation, weather patterns, and energy distribution across planetary surfaces. Ground-based astronomy has not stood still in this revolution. The Extremely Large Telescope, or ELT, under construction in Chile's Atacama Desert, will feature a primary mirror 39.3 meters in diameter. This massive light-gathering capacity, combined with advanced adaptive optics systems, will enable direct imaging of smaller, rocky planets around nearby stars. The ELT's unprecedented resolution will allow it to separate the light of planets from their host stars, potentially revealing surface features and atmospheric characteristics. The PLATO, or Planetary Transits and Oscillations of Stars, mission, scheduled for launch in 2026, will revolutionize our understanding of planetary statistics. Unlike previous surveys, PLATO will focus on bright, nearby stars, making follow-up observations easier. Its unique design, featuring 26 individual telescopes working in concert, will provide unprecedented precision in measuring planetary radii and ages, while simultaneously studying the host star's internal structures through asteroseismology. The Aerial, or Atmospheric Remote Sensing Infrared Exoplanet Large Survey, mission represents another leap forward in exoplanet characterization. Scheduled for launch in 2029, Aerial will conduct the first chemical census of a large, diverse sample of exoplanet atmospheres. Its specialized design focuses exclusively on atmospheric characterization, allowing it to build a comprehensive database of planetary atmospheric compositions across different stellar environments. Advanced coronagraph technology has emerged as a game-changer in direct imaging capabilities. New designs can now block out starlight with unprecedented precision, achieving contrast ratios of better than 1 part in 10 billion. This advancement allows telescopes to detect planets that are billions of times fainter than their host stars. The technology incorporates deformable mirrors that can adjust thousands of times per second to compensate for atmospheric turbulence and optical imperfections. Artificial intelligence and machine learning have transformed the analysis of exoplanet data. Neural networks can now sift through massive data sets, identifying subtle patterns that human observers might miss. These systems have proven particularly effective at identifying transit signals in noisy data and distinguishing genuine planetary signals from stellar activity and instrumental artifacts. The future of planet hunting will increasingly focus on characterization rather than just detection. Technologies under development will allow us to study planetary atmospheres in unprecedented detail, potentially revealing signs of biological activity. The combination of multiple observation techniques will provide increasingly detailed views of individual planetary systems, while large surveys continue to improve our statistical understanding of planetary populations. As we move forward, the emphasis shifts from asking, "How many planets are there?" to "What are these worlds really like?" The next generation of planet hunting technologies promises to help answer these deeper questions, potentially revealing the first definitive evidence of life beyond our solar system. The search for life beyond our solar system represents humanity's greatest scientific endeavor, combining aspects of astronomy, biology, chemistry, and physics into a new discipline, astrobiology. Unlike our search for simple planetary bodies, the hunt for extraterrestrial life requires us to look for specific chemical signatures that could only be produced by living organisms, while remaining open to forms of life radically different from what we know on Earth. Biosignatures, the chemical fingerprints of biological activity, exist in various forms. The most promising is the combination of gases that shouldn't naturally coexist in an atmosphere. On Earth, the simultaneous presence of oxygen and methane is maintained only through constant biological activity. Without life, these gases would quickly react and disappear. Similar chemical disequilibrium in an exoplanet's atmosphere could provide compelling evidence for biological processes. The concept of biogenic gases has expanded beyond traditional oxygen-methane combinations. Scientists now recognize dozens of potential biosignatures, including phosphine, which gained prominence in 2020 during investigations of Venus's atmosphere. Complex organic molecules, particularly those showing seasonal variations, could indicate biological processes. The challenge lies in distinguishing these biological signatures from potential abiotic processes that might mimic them. Surface biosignatures present another avenue for detection. The red edge, a sharp change in reflectance at near-infrared wavelengths caused by vegetation on Earth, serves as a model for how alien photosynthetic life might be detected. However, alien biochemistry might utilize different pigments adapted to their star's spectral output, creating unique spectral signatures we must learn to recognize. The possibility of silicon-based life has moved from science fiction into serious scientific consideration. While carbon forms the backbone of Earth's biochemistry due to its ability to form complex, stable molecules, silicon possesses similar chemical properties. Under different temperature and pressure conditions, silicon could potentially form the basis for alternative biochemistries, particularly on high-temperature worlds, where carbon-based life would be impossible. Alternative solvents to water have emerged as a crucial consideration in the search for alien life. While water provides an excellent medium for Earth's biochemistry, other liquids could serve similar functions under different conditions. Methane lakes, like those on Saturn's moon Titan, could potentially host life using hydrocarbons as a solvent. Ammonia, with its lower freezing point, could enable biochemistry on much colder worlds. The energy sources available to potential alien life extend far beyond photosynthesis. Chemosynthetic organisms on Earth provide models for life that could exist without direct stellar energy, utilizing chemical gradients for energy. Such processes could support life in the subsurface oceans of ice-covered worlds, or in the atmospheres of giant planets where traditional photosynthesis would be impossible. The timescales of alien biochemistry present another fascinating consideration. Life in extremely cold environments might operate at much slower rates than Earth life, making it difficult to detect through short-term observations. Conversely, life in high-temperature environments might operate at accelerated rates, potentially evolving and adapting more rapidly than Earth organisms. The concept of a shadow biosphere has gained traction in astrobiological circles. This theory suggests that alternative forms of life might exist alongside traditional life forms, but remain undetected due to fundamental differences in biochemistry. Understanding how to detect such alternative biochemistries on Earth could prove crucial in identifying alien life. The implications of discovering extraterrestrial life extend far beyond science. Such a discovery would provide crucial context for understanding life on Earth, potentially revealing which features of terrestrial life are universal and which are contingent on Earth-specific conditions. This understanding could transform our approach to biology, medicine, and environmental science. As we continue the search for life beyond our solar system, we must maintain a delicate balance between the constraints of known chemistry and biology and openness to possibilities we haven't yet imagined. As we conclude this journey, creating comprehensive documentaries like this one requires extensive research, countless hours of production, and significant effort to ensure we bring you the most accurate and up-to-date scientific information. If you found value in this exploration of Earth 2.0 and the search for extraterrestrial life, please consider supporting Space Mysteries by liking this video and subscribing to our channel. Your support helps us continue producing in-depth content about the mysteries of our universe and humanity's greatest scientific endeavors. Until next time, keep looking up and wondering what's out there. The universe is vast, and we're just beginning to understand our place within it.